Hello. We've been looking at trying to get a good description out of these objects that we've been looking at, and so far we've managed to get a boundary that wraps around the object. What we're going to look at today is how to take that boundary and turn it into a more compact description, that is to say, a set of straight lines. There's been a long history of people working on curve segmentation in the computer vision and image processing field. And we're not going to go through the full version of it. We're just going to look at a very straightforward and commonly known algorithm. And all we're going to get out is a set of straight lines. But one could also deal with curved boundaries and things like that. We're just not going to do it here. The net outcome is, instead of having a long list of the pixels that goes around the boundary, we're going to have a very short list of the straight lines that make up that boundary. Well, hopefully short straight lines. So here is our sort of prototypical example. We've got a bit of a curve, that's the dark line right here, stretching from x to y. And we'd like to break it up into a set of straight line segments. Now you can look at them and you can sort of see, oh, that's obvious. Here's one, here's one, here's one. But we have to be a little bit careful about how we describe this shape and the algorithm that works on it, so that the computer can deal with it, because the computer at this moment is just dealing with a list of pixel coordinates describing each of the individual pixels along that line. The core of the idea is that we take our set of points and we draw an imaginary line from the first point to the last point. So that's this dotted line right here. And for each of the points along the real boundary, we look at the distance between the real point and that dotted line. So that's the perpendicular distance. Here is one extreme point right there, here's another extreme point, and so on for every one of the pixels along the line. Once we've done this, once we've found all of the distances, we then take the point which is the farthest away from that line. So that's this point Z right here. And we now use what's called the recursive step. We take our original set of points, which goes all the way along here, and we now break it into two sets. One set that goes from x to z, and a second set that goes from z to y. Once we've done this, we've broken the problem into two smaller problems, and we can apply the same algorithm again for each of the parts independently. Z to y is a nice straight line, so when we do this, it's going to come up with a straight line. X to z is, as we draw the line across here, you can see there will be a point here that's a substantial distance. Therefore, we'll select that point as the segmentation point and break it up again into two smaller sections. And then we'll recurse again. And once we recurse again, then we'll find the three straight line sections as the output. So that's the general concept, and now I'm going to go through some more of the details of that. First of all, we need to work with the whole set of points. So our set of points actually is a boundary which goes all the way around the object, and the algorithm that I described to you really works with just a broken up segment that goes from one point to another point. So we need to somehow take our closed boundary and break it up. Well, this is a bit of a heuristic algorithm. That's a kind of theme that we're going to have encounter a fair number of times throughout this series of lectures. You have a core idea, it's nice and straightforward, but you often have to wrap a lot of infrastructure around that in order to be able to get to the point of using the simple algorithm. In our case, we're going to start with the image. We can scan through the image and we can find the leftmost point on our boundary of curve. We can find the rightmost point on our boundary of curve. And that gives us a set of points that we can now work with, because we can break up our original curve that went all the way around into two pieces. The first half goes from A to B, and then the second half goes from B to A back. And then we apply this algorithm that we just went through. We put the line through the current segment, we find the farthest away point. If that distance is less than a threshold, we say that segment is already finished, it's already a straight line, and otherwise we recursively split that into two subsets and carry on with the algorithm again. Let's exercise a little bit of MATLAB. So here's a bit of MATLAB function recursive split. We have our pixels in two arrays, row and column, R and C. Here's our distance threshold. We're going to return our result in a couple of variables. This is the number of lines, and this is going to be an array that has the lines in it. We need to know how many data points we have, so we look at the length of the row array. That's this next statement here. We need to find a vector which goes through all the points, and also a vector which is perpendicular to that straight line. So we look at the last point and the first point for the column and row. We've sort of swapped these around a little bit. Notice last and first, whereas this is first and last. We've swapped them around. This gives us a vector which is perpendicular. We want to make it a unit vector. So we find the length of that vector using the norm function and divide it into the vector. That gives us a unit vector. So now we've got all our preliminaries and we're ready to go through and find the furthest point, max distance. That's our distance to the furthest point. We're going to step through all the points from one to the other. Here's the vector from the current point to the first point on the list. And then we dot product it with this perpendicular vector. That gives us the distance of that point away from the line through that first point and the last point. That's our distance. If our distance is bigger than the current max distance, we save that max distance, save the index of it. That gives us, when we finished all this loop, that will give us the index of the point which is furthest away. Well, it also gives us the maximum distance, and if that maximum distance is less than a threshold, we know that it's just going to be a little bit of noise. We didn't say 0 because data always has a bit of noise to it, so we need to have some kind of a threshold in there. And so if it's less than it, we save the line in our array and we increment to the number of lines that we found, and otherwise we split that data recursively. So the first bit is from the first point to the max index point, and the second bit is from the max index point to the end of the list. And then we just carry on until this list is filled up with all the straight line segments. The part that we've been looking at is shown right here. Here you can see the boundary points. The little stars or asterisks on the corners are the points at which this algorithm has found where it's split up the data. So these are the straight line segments. You can see on this bit it's done really well. On this bit there's a little bit of extra points along here. In fact, if you look carefully, you'll see that this corner right here isn't really a very clean corner anyway. It kind of comes down and it goes a bit like this and then it goes like that. And the reason for that is that when you took the picture of the object, there's a bit of a shadow on the object. So these first points right here are the actual true points on the boundary, and these other ones here have arisen because of a bit of shadow. But everything will be okay. We can deal with that. Okay, so we've got a bunch of long segments, we've got a couple of little noise segments, and we've got really a much more compact description of the object. Before we had a list of several hundred points, 400 or 500 maybe, and now we've got just a set of endpoints. There's 2, 4, 6, 8, 9 lines which describe that object. Here are the length of all those lines in pixels. And if we look at, if we can go back to the image and measure by hand where the real endpoints ought to be, and we can look at how long they really ought to be, you can see some of these segments have actually been found quite closely to the correct distance. You can see right here. This is the one which got broken up, and you can see it's a bit shorter than the true length. That's this one along here. You can see there's a shorter segment, and then there's a couple of little extra bits. But still, we're going to be able to work fine with all of those descriptions right there. Well, this also gives us an idea of we're going to have to deal with as we work down the line a little bit to the rest of the algorithm. We've got lines which are a bit longer than they ought to be. We have lines which are a bit shorter than they ought to be. We have a few maybe broken up lines. Maybe we might even have a few missing lines. So we're going to have a matching algorithm that deals with all of that. Just to give you an idea of how well this algorithm works on a larger set of data, here's the set of all of the samples that we're going to be looking at. We've got 3 different shapes. There's a T shape, there's a thin L shape. Notice it's thin because this bit here is thinner, and here's the thick L shape. And you can see there's quite a lot of really good straight long lines, but on the other hand, almost all of these shapes have a few short broken bits as well that we're going to have to deal with. They're all in different orientations and positions as well. So this is a very simple boundary segmentation process. We've managed to take a set of boundary listing several hundred points around the object. We produced a much more compact type description. It's also conveniently in a set of straight lines, which allows us to go to the matching phase with the same type of descriptions that we have from the model. The model is a set of straight lines, so we have the same vocabulary, makes the matching easier. We also have to take note of the fact that we've got a few extra problems. Okay, we may have some extra segments, and some of the segments may be a little bit too long or too short. So our matching algorithm is going to have to deal with that. So what we've learned here is really an example of a typical curve segmentation algorithm. We've only dealt with straight lines here. We could adapt this for other types of segments as well, circular arcs. This is an example of one of the kinds of algorithms that you might say we started pixels, we started image individual coordinates and descriptions, and we went to a more compact type description. We'll see many examples of that as these lectures carry on. Thank you.